Hey, welcome back to Book Club. And this episode I'm going to refer to as the no cheating allowed episode. Okay, so this is the chapters 9 and 10 in Panton. What I mean by cheating is so many times, as is appropriate, this is actually not a complaint. When we say we're going to ignore this, we're going to ignore this, we're going to ignore this, it really is to simplify and cheat some of these concepts. But those words ignore, if you want to be particular, are saying we're ignoring something because it's small with respect to something else. And all of that, now that we know non-dimensionalization and we know kind of what we're going to do today is actually really walk through all of these equations, and then we can ignore something, we're going to look at a non-dimensional number and take a limit of it. Okay? And so things like Mach number will be an easy one. Like, so the limit of Mach number going to 0 is incompressible. So we're going to start here with kind of all the fluid equations. I'll write them up, and I got my notes. I'm going to have to be looking heavy in my notes to be kind of track all the I's and the J's and things like that. Okay? But just starting off with conservation of mass, 1 over rho, d rho dt. Okay? Remember, that's the materials derivative. And that's equal to negative del I ui, even for compressible flows, right? Because the materials derivative has got the sort of the advection of it, and this would be the other portion of it. And right, we know this is this is, I'll do in green, is equal 0 for incompressible, but we're not there yet. This is just a reminder. So we have this first equation. Now that's conservation of mass. Now density is a function of pressure and temperature, and that's going to come from thermo, right? So you go back to some of the thermal lectures we've had, right? That density, or if you will, specific volume, when we're in a thermodynamics class, or we're talking in thermodynamics language, it's a state variable, and it can be described by 2 different things, pressure and temperature. Now, thermodynamically, it could also be, temperature and entropy, and all these different terms, but for sure, it's at least a function of 2 variables, and we'll use its function of pressure and temperature. So when we also then take a look at this material derivative, we can say the following things. Well, that could also be, if it's a function of pressure and temperature, then we could say this is alpha d rho d pressure. P rho d time material derivative. And then the convention here is to say minus beta d temperature d time. Okay. So where alpha, this is called isothermal compression. And alpha is defined as 1 over rho, and then partial of rho with respect to pressure at temperature. So effectively, what that would do is come over here and basically undo the partials. Okay, and then beta, this is bulk thermal expansion. All right, and so beta is then similarly defined as 1 over rho, and then the change of rho with respect to temperature when held at a constant pressure. Okay, so that would come from thermodynamics. Now let's look at momentum. Momentum is density, the material derivative of the ith velocity at time, and that's true again for both compressible and incompressible. And then negative pressure gradient, we have the jth derivative of the stressed tensor, and I'll include in here rho gi. So gi, gravity being a vector, it's going to, any kind of buoyancy forces, which can drive things, right? But buoyancy, you can get natural convection and things like that. Okay, we've actually covered last time the full stress tensor, and so now we can put in that. So knowing that del j tau ij actually becomes minus 2/3 the ith derivative, and I'll be intentional here in keeping viscosity inside of the derivative, because viscosity can change in terms of viscosity can change spatially, right? Like we've talked about all those weird kind of viscosities that can happen. But primarily, even here, you have to watch out. Viscosity can, in fact, the most primary thing it changes on is temperature. And so, in fact, when we get to conservation of energy, if we have a fairly large temperature swings, then you would have to come back here and adjust the change of viscosity to temperature and any gradients that would show up there. And then I'll have to be really careful here. My 2's and my del's are horribly close. That's 2 times the derivative, the jth derivative of mu Sij. I've never figured out how to make my 2's not look like my del's, so I'll try not to cross it. I don't know. All right, so that's that would then be again the full stress tensor here. So that's referring to this portion. All right, and then we have conservation of energy. So I'll put dashed lines again, and remember we actually derived how you could take the full conservation of energy and then subtract out the kinetic energy portion coming from the momentum equation, and then what you get left with is now a transport equation on temperature that we still kind of refer to as conservation of energy, because all that mechanical engineering is already taken care of by momentum. So then we have rho Cp, and then the material derivative of temperature with respect to time. And then this is one where we also get a couple more terms that we've shown so far. And so this has both the derivative of thermal conductivity K, and then the jth derivative of temperature. So again, allowing for the fact that thermal conductivity may change with temperature or anything. So it's sort of buried inside, so it's not just a pure conductivity times the Laplacian. And then plus a term that we'll just call capital Phi for now, and this is actually the viscous heating. Okay, and it's not a secret. So I'll just write it down. Viscous heating. We'll talk about that in a second. And then plus term beta times temperature, and then the material derivative of material change of density with respect to temperature. Okay, and this is the one that can also kind of create thermal convection. It's important there too. So, in terms of the transport, right, if you're solving for temperature, this term shows up, right, from kind of pulling from out of here, if you will. Okay, so let's talk about viscous heating, and I'm going to first write it down in sort of its standard tensor, not like Einstein notation. And so that's where you get, and that's why we've gone to Einstein notation. So that is the shear stress double dotted with the strain rate tensor. And again, right, there's kind of like vectors and dots and all stuff. It really loses its power, and you get super confused. And so that's why we don't do that stuff. And that's why that Einstein notation is powerful. And so what this really means is minus 2/3. If we sort of expand out, it's mu, and then you get the divergence portion squared plus, again, that's a 2 mu, and then Sij. So i's are summed here, and then it's squared. So that's a number. It's constant, a scalar. That gets squared, and then this is again sum over I, sum over j, and so that thing also shows up. So viscous heating, where do we see it? Gosh, here at Venus, we're trying to go fast. That's one of the terms that causes you have. It's not just the stagnation temperature of air when you're going like Mach 4, but it's also in that boundary layer at viscosity. Like it's the viscous heating that's happening right in that boundary layer, which is then adding heat to the surface. And so that's part of what gets things hot. And so in fact, when people ask what's the definition of hypersonic, usually we stick to this very simple answer, which is like Mach 5 or above. The more official answer is it's the speed at which heat kicks your ass. Because you could be flying Mach 3, say at sea level, and it would be super, super toasty because of this term. Because you're in thicker air, And so this term shows back up in terms of a heat flux, right? So the heat flux is going to have, there's your air density, and then it's going to come in and it's going to pick it up. So it matters. This is certainly a term that matters in hypersonics, right? And so that's the full set of equations. And so then what we're going to do over here is sort of write what happens after you then non-dimensionalize. And so, because I couldn't possibly do this on board, you'll see there in chapter 9 and chapter 10 for pen, so go walk through. But ultimately, non-dimensional variables we're used to so far. Well, I'll keep it low so I don't completely block it. So we're used to Reynolds number. That's a rho, some sort of characteristic velocity, some characteristic length divided by viscosity. And again, you're sort of free to pick whatever that happens to be. If it's a boundary layer, usually that's the free stream velocity. If it's a pipe and the L is actually a diameter, sometimes about boundary layers, it's the distance. You got to be careful. Anyways, you pick a length scale and sort of stick with it. And so that's one. Froud. This is actually the, G over whatever that characteristic velocity squared. So in fact, I'll use that as a V0. Froud. This is going to take care of sort of gravity waves and things like that, right? This is effectively what's going to come modify this term up here. This sort of density gradients and gravity affecting it is going to show up here. When we do this and actually include surfaces like between oceans, Froud number is actually a very important one that can give very different characteristics. It's a beautiful Froud versus Reynolds number map that ship wakes create all these different interesting patterns depending on it. So that's one. Right? We've already talked about another one. Mach number is that characteristic velocity divided by the speed of sound. Here I'll use A for speed of sound. Sometimes use C. Right? And then also in this notation, and I know we've derived the speed of sound before, and so I'll actually write here gamma RT if it's ideal gas, but more generically, you can think of this as gamma naught over beta alpha naught. And what's beta naught and alpha naught? I'll write it here in a second. Effectively, it's some sort of reference ratio specific heat and some sort of reference coefficient of compression, isothermal compression. Okay. And then there's a Prandtl number, which is going to relate viscosity to that isothermal compression. Right? And then two numbers I'll use here. And by the way, this alpha, we'll actually get into it, but it does relate to decay here as well, and viscosity. So a lot of times you'll see that once you sort of divide through, I'll just write it here. Alpha is K over rho Cp. Okay. It's sort of the thermal diffusion, if you will. And so the Prandtl number is then relating that thermal diffusion to the viscous diffusion, and that's a nu, not a velocity, nu. Okay, and then we're going to need two terms, A and B, and they're not attached to anybody's special name, but this is alpha naught, rho naught, Cp naught, T naught. So that's just a host of sort of reference values for each one of these, and then beta is going to be a reference value for beta naught, T naught. So again, it's not necessarily non-dimensional number, it's just a sort of a grouping of these things. So that'll make this next column a little bit easier. Okay. So what we have seen so far, and I'll just sort of write that down so it's not confusing. So far, what we've done for the most part, when we're talking about an incompressible fluid, we're talking about two things. Specifically, we're saying that gamma naught Mach squared is effectively far less than 1. Now, I put that there because this is normally the term that shows up, and for you to ignore something, that needs to kind of go away. And so what ends up happening, if you say, well, what does that mean? Okay, this is where the specifics get interesting. And so if you then come back and say, all right, well, much less than, I at least want it to be a tenth. So maybe what you really mean is gamma naught Mach squared If it's a tenth, then I'll be happy. Okay. And so if gamma is 1.4, then maybe you're saying, well, Mach, and you kind of do the square root. Basically, what you end up saying is Mach is less than 0.3, I'll be decently happy, right? And so that's where that comes from. So if you've ever heard that, hey, for Mach numbers less than 0.3, you can treat it as incompressible. Well, that's where it's from. Okay, 0.3 it sounds like a weird number, but it's actually because it goes back to the gamma Mach squared as being roughly a factor of 10, less than 1. So does it mean you can ignore it? I mean, a tenth doesn't sound like it's a big deal. So maybe a hundredth, you'd be very happy ignoring it. Well, for the most part, when we're doing sort of calculations and things like that, right, you're just trying to be in the right, I won't say right ballpark, but it's a calculation, right? You would never. It's why you still have to go to wind tunnels and things like that. So that's a pretty good approximation that you're going to stay in the incompressible world with air or whatever gas you're talking about. Okay. And so where this ends up, so we'll come back to this kind of thermal equation. And so what you end up having here is 1 over rho d rho dt. And that's equal to, if you do all the work, that's a gamma naught Mach squared times alpha d rho dt minus Prandtl b beta over a dt dt. Okay. So one more thing. So far we've been doing that, so you can see that term here. But the other thing that we've been doing, just to be complete so far, is that we've also been ignoring all the variation of these parameters. So what does that mean? Basically, this inclusion would say incompressible, and then we would do some silly thing that, like saying that the density and non-dimensional acidic heat and non-dimensional viscosity and non-dimensional bulk thermal expansion. So that's an alpha. Thermal expansion, viscosity, and conductivity are all not changing. That's what that statement means. Not that they're equal to each other, but each one has a value of 1. So they're not changing. You non-dimensionalize density by whatever you're doing, it's equal to 1. You non-dimensionalize thermal conductivity by its initial conductivity, it's 1. So that's usually what we've been doing so far. So you can see here, step 1 for being incompressible would be this number goes to 0, right? Because that, as a reminder, that's still also equal to minus del I ui. So if this is 0, then that is 0, which then drives the whole thing. Okay, on the momentum side, you would have, and I'm not putting stars here, but these are all effectively non-dimensionalized now. So rho, and then material derivative of the ith velocity with respect to time, a negative del I p plus del j tau ij plus rho g over Froude squared. So these are all have been all non-dimensionalized, and so this actually backs out. Okay, and then normally you would see the del j tau ij expanded, and that's where Reynolds number pops in. So 1 over Reynolds, and then you have minus 2/3, and then that viscosity del I ui plus 2 del j mu sij. So nothing new there. Okay, and then on the energy side of things, this is where you sort of collect all these other terms. Rho, Cp, and again, these are all kind of the non-dimensional versions of that. The transport of temperature, and you get a 1 over Reynolds and Prandtl times del J, and then again, sticking the K in there in case there's a change in thermal conductivity, plus there's your viscous heating, plus beta B 1 over Prandtl and almost couldn't read that, gamma Mach squared over alpha times T, and then d rho dt. Okay. And then where again, this viscous heating is the undimensionalized version, length scale, viscosity, and velocity squared. Okay. So that's a lot of writing. So sorry for just sort of making a kind of pooping over this board. So go read through this chapter 9 and 10 with Panton. But the important part here is that, again, we're trying not to cheat anymore. And so what is not cheating anymore? It actually means being very clear what we're ignoring and why we're ignoring it. And so if we say incompressible, for instance, what we're actually going to mean is gamma log squared is smaller, much smaller than 1, which will translate usually for air. That's usually the one we're concerned about. For air, it would be enough to say I'm in air and Mach is less than 0.3. That would be enough for incompressible. And then when you're saying, for instance, right now, like all of these variables are actually buried inside, you would specify, no, my thermal conductivity is not changing with respect to time or spatial dimensions, and it can pull out, things like that. The Prandtl numbers, when you go kind of walk through it, Prandtl numbers, can be very different for like a liquid metal, for instance, versus water. Okay, so you can do a lot of interesting things with Prandtl numbers. For the most part, for kind of waters and fluids, Prandtl numbers are going to be fairly constant. And so there's some fairly easy models of that. And so you don't have to just you don't have to remember constant. And then really, all of the rest of these kind of big main variables do end up playing a role. So Froude, like I said, I already mentioned, in boats, that's more like free surface flows. But one of the ones that you will see Froude show up on is, again, natural convection. And so that's actually where the only thing that you're letting density change is with sort of temperature, and you can get a buoyancy force that shows up. And so you can actually solve for when does buoyancy kick in, and one of them, you can do it with this Froude number, or there's another number that's called the Grashof number that basically buries this in there too. So if you've taken a course in heat transfer, that would get into it. I'm not going to get into that stuff now, because really it's almost just kind of a converging of all of these variables, and then going for that. I used to say when I was teaching in my classes, I had hope when you start, especially in heat transfer, you see all these different like non-dimensional variables that are just recastings of existing non-dimensional variables. And I used to say, hey, there's hope I'll get a Duggleby number sometime, because you just take this non-dimensional number to that power, this one to that power, and you can create a new thing. So I'm being a little flippant, but the world of heat transfer, again, it's one of those fields that's actually fascinatingly complex. And then by the time you try to break it down to like, no, I'm trying to do something really, really simple, then it's just like look up tables of all these correlations. So to me, the fun is actually in the crazy stuff. But thank goodness there's nice lookup tables. Okay, so that's enough. So like I said, this is sort of the no cheating allowed. So walk through this. You have the math now, and you're reading these two chapters. It's why Panton, again, it's that sort of, as a mathematician who happens to be in fluid mechanics, right? Panton was kind of being very clear about what assumptions we're doing and why. So that's, again, part of the reason I really love this book. And that's why you would never show any of this math at kind of that undergraduate level. It's sort of too much. But when you get out into the real world, again, like all of this stuff really starts mattering. I mean, even things like ideal gases in the rocket world are not true at certain pressures and temperatures. So, the reality of where things come in, where viscosities or thermal conductivities are changing, are super important. And you have to know when you can ignore them and when you can't. Otherwise, you'll be your solution space will just be completely wrong. So, all right, this is the No Cheating episode. We'll see you next time.